Mr. Reynolds, take it away.
Okay. Well, thank you, Leigh for Broadhurst for giving a presentation tonight. Our speaker for tonight, Dr. Leigh Broadhurst, holds a Ph.D. in planetary geochemistry and physical chemistry from the University of Arizona, and a Bachelor of Science degree in geology from the University of Maryland. Her geological research has been focused on rocks of the mantle and origin that helps categorize the origin of Earth and the plate tectonic system. I met Leigh at our Montgomery County group, and she has given some fantastic presentations in the past, and as well as to our group. And with that, I'm gonna turn it over to Leigh. Mute.
Okay. Hello, everybody. I'm very glad to be here this evening, and good evening to you all. And this presentation is going to be about rare earth elements and the mineralogy, and also the some of the mining and the geology background for the rare earth elements. I don't want to spend a lot of time showing you things that you can pick up on the internet, but we will start with a brief introduction. So let's see if this works again for here. Share screen. See if, are we okay?
We're fine. Thanks, Leigh.
Okay.
Yep, doing great.
So, gonna move this down a little or up. I don't think you guys see this, do you?
No.
Okay, rare earth elements are defined as lanthanum to lutetium. There's one kind of exception in here, which is promethium. This is a man-made element that comes from a super collider, and it only has a very short half-life of seconds. So we don't find that in geology. And then added to this is yttrium too, which is kind of underneath here. Why these guys are here in the row here is because we're filling the 4f electron shell. So all of these elements are very, very similar and have very similar ionic radius. And that's why they got the name rare earth elements. The rare came because people at one time thought that they only came from a certain area in Sweden. And earth came from the French word terre, which meant oxide. But actually, these elements are not as rare as platinum group elements or even gold. They're fairly common, but the problem with them is that they're very, very hard to separate from one another. So the separation technology is a whole different bag of worms, and we won't worry about that because we all are interested in minerals here. And so let's see if I can go to the next. Okay. So this is what we need rare earth elements for. And it's a lot. Okay. The most important thing is these phosphors. We have all gone to our away from incandescent lighting. We go to LED lighting and other types of things. And we also have all these bright colors, the colors that you see on your computer screen, the colors that you have on your cell phone, the different types of Christmas lights you have now are very, very complicated compared to what they used to be. And then, of course, we have the magnetic things. You all have probably seen, for instance, world's strongest magnet on Amazon or something, and niobium magnets. But we have, look at all the different types of things. Anytime that you're going to generate electricity, you're going to need a magnet. And anytime you want to generate a tremendous amount of electricity in a very, very small location, or such as in an automobile, you're going to need very powerful magnets. Ceramics we use too. Lots of different ceramic technologies and glass polishing. And one of the things you'll notice when we get to looking at some of the minerals is that you'll see again and again and again, we see these very deep red colors that come in, and that's some of the phosphors. To get these red colors, sometimes you need very high molecular weight elements. You're just not getting them with the light elements. Batteries, petroleum. This catalyst is probably the #1 use for these rare earth elements. We don't it's not as obvious for us, but petroleum refining and catalytic converter and all the different types of organic compounds that we need catalysts for. And defense is the primary reason why this has become so important lately. We'll go to the next slide here. Which shows you that these are some of the uses for them. You can see catalysts are the major use here in the orange. And you also see that regardless of who you consult, the leading producer of rare earth elements by a long shot is China. And this is disturbing for Europe, it's disturbing for Canada, it's disturbing for the United States. We don't ever like anybody to corner the market on something because catalysts are so important, and so are our technologies such as the cell phones and our defense technologies. And so the overwhelming consensus from all the Western countries, and in fact even China, is that this has got to change. And so we are on the lookout for reopening mines, finding new resources, and finding new ways to mine these elements and separate them from each other. Okay, so let's find out something about where the rare earth elements are and their mineralogy. One of the first places that we go to find these is shield rocks. And so shield rocks are, you see here, there's Canadian shield and up in Greenland, Brazilian shield, Antarctic shield. A couple places in Africa, of course, South Africa is famous for this, your platinum group elements. Mining is very popular, of course, in Australia. And you have your Baltic shield here. In many cases, these old rocks have been exposed by repeated glaciations. There's plenty of shield up here in Russia too, but a lot of this is still covered with glaciers. So shield rocks date back as far as 4 billion years, and these are very, very ancient metamorphic rocks exposed by glaciation and prolonged erosion. Okay. So we're going to go, I was very lucky to have this topic. I didn't even realize that my travel during this year has going to play a heavy role in this lecture, because I actually went to this place where the rare earth mines are, and I had no idea at the time that it was going to be so. It wasn't the reason I chose this topic at all, but then I realized how fantastic it was going to work out. So here, in a close-up of our Canadian shield, we're going to look here at the Slave Province. The slave terminology, here you have Great Bear Lake and Great Slave Lake. It does not mean slave as in somebody who's your servant. It was an Indian name, and they didn't pronounce it correctly, and it just turned into slave. So we're looking at the Slave Province, which is very old, and this is in Northwest Territories. And so here's the Great Slave Lake down here, and that's where we're headed. This shows you a picture of what it's like. The Great Slave Lake is the size of Belgium. It is enormous. Just a tiny, you can't get around except by aircraft. Even a boat will exhaust its resources because the overwhelming majority of the lake has absolutely no fuel. It has nothing on the shore at all. So if you're not in the town of Yellowknife or one of the small other towns there's one other town on the lake that you can get some fuel, that's about it. So here you can see some of these nicer houses are up on these rocks. Every single rock in this area is glacially striated. Here's some of the striations here in one of their local parks. This is what it's like. There's some very thin soil with a lot of pine and spruce trees. And this is one of the places where there's a little bit of relief, a beautiful waterfall. You can see the people here about this size. And this is about the maximum amount of relief that you find anywhere in the Northwest Territories. So all the action is around the lake shore in the town of Yellowknife. You may be familiar with that if you've ever watched one of the ice pilot shows that takes place. So Yellowknife is named Yellowknife because of the yellow knife, the gold knife. Gold mining has gone on here since a long time. This is a little bit of their mining museum, operating in the north since I think it's 1947, the giant mine. A lot of the gold mines are still operating. A lot of them are closed because of the use of arsenic, and it's it was leaking into the water sources for the lake, and the Canadian government said enough of this. But as people were prospecting in these ancient, about 3 billion-year-old rocks for gold and other things, they came across other minerals, rare earth minerals. Here's some of them, just the old ore cars. We'll go through this quickly. And this is their explosive shack. This is where they had all the explosives for the mine, and they have it restored there for you. Okay, so here we are at the edge of Great Slave Lake, and this is the Nechalacho mine. The Nechalacho mine is the newest mine that's come online. It's been talked about for quite a while, but now the Canadian government, in consortium with the native community in the area, has started a big mine here. So it's right on the shore of the lake, and it's by a little native town called Detta. And the native people, so this shows you, this is your huge Great Slave Lake. Here's Yellowknife and Detta, and here's the Nechalacho rare earth mine. These are your only other towns here, Hay River and Fort Resolution, where you can get any sort of diesel fuel or something. So if you imagine from here to here is the size of the country of Belgium, you better be prepared when you go to Yellowknife, when you leave Yellowknife. Okay, so in this rock formation from this mine, here is one of the major minerals that you find in here. And these are ancient metamorphic and igneous rocks. Fine eudialyte, nice example of it. And notice that you have zircon, and you have cerium in here as your rare earth. Zircon is found with the rare earth elements again and again and again and again. We'll talk about that a little bit later, but that's very important. Where you find zircon mineralization is a great place to start looking for rare earths. Here's examples of some zircons, gem quality ones, beautiful. And again, the zircons that come from the rare earth mines tend to be the red ones, just as we'll see with many, many of the rare earth elements. The red seems to be the most popular. So this mine, this area also had zircon, and it had nepheline. Here's a beautiful, this is what nepheline looks like most of the time, but here's a beautiful, beautiful gem quality one that is green, that's either blue or green in the blue. And this is one of the components of lapis lazuli. So what happened at the Nechalacho mine? It's a nepheline syenite. That's the type of rock, Archean age, and it had further alteration, 1871 to 1835, and that's million years ago. So these are billions years. This is 1.8 billion, 1.8 billion. This is your primary ore mineral here, bastnasite. And so the REEs here stands for rare earth elements, because there can be many of the rare earth elements. There's always cerium, but we can have a whole list of other ones in here. And notice this is a carbonate and a fluoride. So here's some examples of this. This is the primary one, but all these hydrothermal minerals are found at the Nechalacho mine. So this is one of the reasons why this is a very, very important resource. And there's plenty of other ones too, but these are your primary ones. But notice here how much you do have some oxides. Yes, you do have some oxides, but you have some phosphates, you have some fluorides, you have some carbonates. It's indicating to you that this is a very unusual hydrothermal fluid. Okay, so Nechalacho is unique and valuable because the basal portion of the deposit is enriched in heavy rare earth elements. So these are the ones that are europium to lutetium, and then yttrium is thrown in there too, just because it acts like that. And of course, their zircon and niobium are very rich. This is our richest known deposit, 9% as measured with rare earth oxides. And this is a picture of some of the other ones here. This is a primary niobium ore here, Fergusonite, and parasite here. Very, very interesting. Carbonate and fluorite. And it can be blue. It can look like this. Again, you see the deep, deep red color, but you can also, I'm not sure this one in the background is parasite. I think it's just this one right here. So why did this happen? Well, these are very, very ancient deposits, the original rocks, and the Earth was very, very much hotter when it formed. And the subduction system that we have now simply didn't exist. To the best of our ability, it just did not exist. You have to realize that the Earth not only was hot from the accretion of all the, can think about asteroids accreting and gravity sticking them together and sticking them to sticking together until something becomes so big that it differentiates into a core, a mantle, and a crust. It's so hot that it becomes molten. But also there's many, many radioactive elements that have short half-lives. Aluminum 26, for example, I think it's 26, I think it's 13,000 years or something. So there's a lot of heat from the formation of the planet, but there's also a lot of heat from radioactive elements. And when it's gone, it's gone. It doesn't come back. So the conditions for these rare earth elements in these ancient Archean crusts, in these ancient shield rocks, they simply don't exist today. And this gives you kind of an idea. We'll go through this. This is your typical subduction zone. The best known one in the world would be the west coast of South America, where you know that you have the Peru-Chile trench that goes all the way up and down the coast of South America. You got the oceanic crust that's going down. It's filled with sediments. It's filled with fluid. It acts as a flux about 200 kilometers inland and about 200 kilometers down. What do you get? It melts and you get the volcanoes. This is the Andes. And then you get a lot of folding and thrusting, and you get a lot of crazy stuff going on the shoreline. But generally what we have today, because this oceanic crust is so heavy and so dense by the time it gets over to the subduction zone that it goes down fast. Low angle subduction is what we thought was going on when there's very interesting shield rare earth element deposits, and notably deposits such as some of the platinum group elements that we have in South Africa, and gold, very, very large gold fields and very, very large diamond fields that are just not reproduced today, is that we had low angle subduction because this was much hotter, much more buoyant crust. And you see there's no volcanic arc. It just kind of pushes in and you get a bunch of these rifts. And of course, if you go up there, you have to get the pictures of the aurora, right? So that was looking out on the deck, and I just made a composite of these things. I wish these folks would have turned their light off, but the aurora is indeed beautiful in Yellowknife, and it's worth a trip. Okay, so here's the most typical mineral that almost anybody has around the house. Introducing it to children, it's everywhere in the world. There's 40, 50, 60 different types, even in one museum location. That would be calcite. You all know calcite. Calcite in a different form as a geode. Calcite is limestone, but we call it a sedimentary rock. Well, what happens? Oh, of course. How could I forget this? Calcite. This is one, just as an aside, this is certain types of storms wash these up, Scotch bonnets, by the bucket load in the about January, February, when you get one of the storms that starts out in the Pacific and it dumps snow in the Sierra and it dumps snow in the Rockies and it dumps snow in the Great Plains and it comes all the way across the country as a strong northwest wind. It pushes all these guys up. But again, these are all calcium carbonate. Well, there is such a thing as igneous calcite. Igneous, and this is a calciocarbonate rock. It's from Magnet Cove, Arkansas. This is from a unique carbonatite magnet rich in molten carbonates. So this is calcium carbonate, this is iron carbonate, this is magnesium carbonate. The same things that we saw, if we go back to the previous one, the same things that are in the shells. Oh, sorry. Let's go. It didn't mean to go there yet. The same thing you saw in the shells, the same thing you did it. And this was not understood for many years, probably for, I'd say, the better part of a century. People just didn't think, well, how could there be igneous calcite? How could this happen at all? This is a sedimentary rock. But that having been said, This is absolutely the case. And this is I hate to read this, but I'll read it. The rise of carbonatites in what we call the boring billion, and this is 1800, so this is 1.8 billion to 800 million years ago, provided most of the world's rare earth deposits. So this is a different one than I just showed you. The Archean one was very, very valuable, but it has a problem. It's a shield rock deposit, and a lot of the shield is really, really inaccessible. If you've ever flown over Greenland, if you've ever been to Greenland, if you've ever been to Scandinavia, if you've ever been to flown over the very northern part of Quebec, where there's and the same thing is true of Northwest Territories. When you get beyond the lake edge, there's nothing but a little pockets of glacial lakes and a swamp. There isn't even a tree. There's nothing. So there are problems with shield rocks. Okay, most of the world's rare earth deposits are perhaps might be in the shield, but the ones that we know about are in the carbonatites, in that unique situation where we have a molten calcium, iron, magnesium carbonate. So the world's largest deposit, we're not going to talk too much about this, in Bayanova, Mongolia, and the second largest in Mountain Pass, California, both date to 1300 or 1.3 billion years ago. And what's interesting about this Proterozoic time period is that it's responsible for just about all the supermassive mineral deposits. Okay, Homestake gold mine, I don't know what it was. It's something like 30 million ounces came out of there. Broken Hills, which you all know way better than I did. I do. There probably half of you or more have Broken Hills samples in your house of some sort. This is a lead zinc mine. It's the biggest Olympic Dam in South Australia in Ketri. Olympic Dam in South Australia is the world's largest copper, nickel, gold, uranium deposit. It's the world's largest. Argyle, Western Australia, the world's largest diamond deposit. This is not the largest deposit, Voisey's Bay in Labrador, but the nickel and copper are incredibly rich. And of course, we have the Thetford mines in Ontario, nickel mine, but that's by all means thought to be an iron nickel meteorite impact. And it was not part of a geologic process that wasn't extraterrestrial, or in terms of a terrestrial geologic process. So at this time, we had the supercontinent Columbia. Here's two pictures of it. They're kind of the same. So South China, Laurentia would be your northern part of Canada. So here's the slave province that we just talked about. We have Siberia, Baltica, Amazonia, West Africa. These guys were all stuck together. And that kind of explains to you why we can have some of these deposits the world's largest, because perhaps the world's largest deposits were all occurring primarily in the same place. And as the continents have drifted and moved away, they have moved these deposits to different continents, but at one time they were much closer to each other. And of course, these are just the best that you can do. We're not quite sure. We're not exactly quite sure what was going on, nor can we be. So what are carbonatite rocks and minerals? Very interesting. Less than 20% silica, less than 20% SiO2. That's almost unheard of. Rocks are always made with silica. That's just the way it is. Okay. They have igneous carbonates, primarily calcium, magnesium, and iron, but of course, there's other things in there too, such as manganese. This is very important. They're almost exclusively from continental rift areas. I showed you that there's more rift pictures coming up, but remember, we thought about that previously with the shallow angle subduction. It causes a lot of rifting as opposed to a forearc basin. And you also have high sodium and potassium feldspars, really, really, really sometimes some of the most pink feldspar you've ever seen in your life. Even though we have all this calcium and magnesium, it's important to realize that this calcium and magnesium and this sodium and potassium feldspars are separate. originate from a melt that's immiscible with silicate melts. So if you can think of two things that don't go together, you know, oil and water, we have a situation where we have two melts that are immiscible. We have a carbonate melt, and the rest of the silicates are separate from it. And so this is the key thing for the rare earth elements. These carbonatites are very high in volatiles, very low in silica, very, very fluid because they don't have all that sticky quartz trying to precipitate all the time. They contain large amounts of what we call large ion lithophile elements that do not fit easily into coordination sites in common rock forming minerals. What is really important about your rare earth elements? Well, they're larger because they're farther down on the periodic table, and most of them have the +3. Okay, they're +3 ions. They're not +2 like calcium, magnesium, iron. They're not +1 like sodium and potassium and barium. They are +3 with the exception of europium, which often has a 2 valence. And this means that they, with their size and their charge, they like to stay in the melt as long as possible. So they concentrate in a fluid melt, and they specifically concentrate in low temperature melts rich in volatiles, which is exactly what a carbonatite melt is. When you have all that CO2 in there, it's a people describe it as a shaken up pop bottle. So this shows you some of the carbonatites in the world. And we're going to talk a little bit about Mountain Pass because that is, we're very happy about the Nechalacho mine being opened up because that gives us a North American option. And here we have a carbonatite REE. Here's your biggest one here in Mongolia. It's Chinese. A couple other places in the world, Vietnam, one in India, pretty big one up here in Kola Peninsula, and a couple down in Africa. We're going to talk about this in Brazil too, because this is a very large and very well-developed mining operation in Brazil that's kind of also as the one in Canada. This is going to be the future. But by and large, we don't see them too much on the Archean craton. You notice a little bit on the edge of it. Yes, maybe. Here it is. A lot of times they're on these Proterozoic rocks or they're on the border of them. So carbonatites occur on all these, where all these black dots are. There's quite a few of them around. Of course, there's more, but these are some of the largest ones. But not all of them have rare earth elements. It's a good place to start looking, but they don't all have them. So when they do have them, what are we looking for? Okay, remember I said these are coming from rifts, particularly carbonatites. Carbonatites come from rifting areas. They don't come from the mid-ocean spreading ridge. They don't come from shield volcanoes or stratovolcanoes. They don't come from island arc and trenches and subduction zones like many of our other mineral deposits are definitely subduction zone oriented. These are rift oriented. And this gives you an idea of what's going on. Keep in mind, I have no idea how to pronounce this, but it's Oldenoyo Lengai. We'll just go with. Keep this in mind. We're going to see it in the next slide. This is the only known location of a carbonatite volcano that actively erupts. We don't have another place on the planet where we have one. Okay, so this shows you the rift situation here. All the tectonic plates always form in these triple junctions. That's just how they do, about 120 degrees apart. So the Gulf of Aden has a rift zone through it. It's already open. The Red Sea has a rift zone that's open. And the Great African Rift Valley here hasn't quite opened up, but it's on its way. It's on its way with these great big lakes here. You can see the size of these lakes is not exaggerated. These are proto-oceans. And sometimes the rifts are very interesting. They actually are, even though it's pulling apart, there's not always necessarily a valley. Sometimes you see, as here, a high part, and all of these are these volcanoes. Okay, so we're looking for carbonatites in a rift zone. And this is just a picture. This is that Oldonio has these great big cones that show up, and they only last a couple weeks or months. They get washed away by the rain. So people thought, well, maybe these there were more of these in the past, but they don't exist anymore. And this is an example of what some of this rock looks like. This particular one is quite greenish. And here's your Mountain Pass mine in California. This has this type of rock in it. It does not have any volcanic rock in it whatsoever. This is in the Mojave Desert, and the mine operated for many years. And these are the type of minerals that we had here. Once again, I brought this back because the primary mineral here again is this bastnasite. It's mostly a cerium mineral here. This is the important thing here is in the carbonatites, we have mostly only the light rare earth elements. So that would be the lanthanum to the europium. The heavy rare earth elements are much rarer, and that's why that Nechalacho mine is so valuable to us, because we get the heavy rare earths. Carbonatites tend to concentrate the light rare earth elements. And here, one of the reasons why is because as the atomic weight gets higher in the rare earth elements, the atomic radius actually gets smaller, because you're adding these electrons to an inner shell. The outer shell is already filled. And so there's actual contraction as the atomic weight gets larger. So the light RE have a bigger ionist radius, and they're even worse lithophiles. They concentrate specifically in the melt. So the major minerals are calcite, dolomite, barite, and fluorite. This is a huge amount of barite here. It's up to 20% in some areas. And these are some of the other primary minerals: monazite, parasite, centrosite, allanite, and samalite. Again, carbonate, fluorine, carbon. Very interesting. And then monazite, of course, is just a basic rare earth phosphate. And even here, the allanite is hydrated. So you can see that these things are all coming from a very, very fluid environment. And this should be familiar to you all, because of this mineral, which you all know and love, fluorapatite, almost always found with carbonatite deposits. And nearly always, when you find fluorapatite, you can look, and you're in a carbonatite, then you want to look around and see if you can find any rare earth elements. What is one of the primary reasons why the Mountain Pass mine is not, they are going through tailings now, but they are not doing active mining? Well, number one, it's in California. Number two, it's in California. Number three, it's in California. So the rare earth elements, especially in fluorapatite and some of the other minerals, may contain substituted rare earth elements. Yes, for the calcium, it happens, but it also can contain thorium and uranium. And the thorium and uranium concentrations can be very, very significant. So bastnite, allanite, zircon, apatite, anslite, fluoride, charoline, and others are hydroxides, fluorides, carbonates, and chlorides that are found in carbonatites. And they can all substitute rare earth elements. They also substitute thorium and sometimes uranium, and they're definitely radioactive. So this is a zircon here, and you see this pleochroic halo in the thin section here. This is radiation damage from the thorium that's contained within the zircon. And here, so we have zircon and we have allanite, and here we have charoline. And again, we see many, many, many times the rare earth elements have this bright red color, and this is what the mineral collectors are looking for, and as opposed to something that's kind of drab like this, and what the prospectors are looking for. And also in certain places, North Carolina, for example, other places in the world, especially Australia, these minerals concentrate in sands. They concentrate in heavy mineral sands, and they have a red color. Quite often the red color is from garnet, But in other places where there's not a lot of garnet washing out from erosion, it's heavy it can be economic enough to mine the sands and separate the rare earth element particles. So this has been a major environmental hazard, and it's pretty much brought things to a standstill. So something has to happen, because we've got to find a source of these that's not China to move forward, and we're going to have to find a way to deal with the thorium, or find other sources such as the one that I showed you up at the Nechalacho mine, which doesn't, because it's not a carbonatite source. Certainly it does have some uranium and thorium, but the levels are much, much lower. So I had to throw this in here because it came up on the internet like 6 times when I was working. So where did they get these vast thorium reserves? Enough to power the country for 60,000 years? That's that Bayan Obo mining complex in Inner Mongolia. So that's looking to the future. This is one of the reasons why people want to start a new era of much safer reactors. So we'll see if that happens. There's certainly enough thorium to power the country. All right, so here's something that you all know and love. Zircons, tourmaline, aquamarine from the famous Minas Gerais in Brazil. The pegmatite is the most famous in the world. And in fact, that state of Brazil is just so incredibly blessed by mineralogy. It's almost unbelievable. These are beautiful enough, but what else does it have to offer? Well, you know that it's a famous mineral locality. I would say that 100% of you have something from this location. And if not, you've certainly seen it again and again and again, and there's plenty of it in the Smithsonian. So this is the Araxá mine, which is late Cretaceous. This is much, much younger than the other things we're looking at. And this is a carbonatite ring. And this is, you can see it on the aerial photo here. You know, never mind all these things. These are just project names. But indeed, there's a ring neck that's intruded into these Proterozoic metamorphic rocks. So the metamorphic rocks have it's an ancient rift zone that was rifting, and it looks like there was probably carbonatites that had come up periodically through time. But this last one in the late Cretaceous came up and is absolutely loaded with rare earth elements. So these are the primary minerals: magnetite, apatite, phlogoplat, carbonates, of course, and pyrochlore, including the very interesting barium pyrochlore. This mine alone produces 80% of the world's niobium. But that primary mineral that we saw before, the bastnasite, it has almost none. It's a different sort of mineralogy. And so here's a picture of the monazite. 70% of the rare earth minerals there at Araxá, as opposed to being the bastnasite, is monazite. So just a basic phosphate. And then pyrochlore here, which is heavy on the fluorine in this particular location and light on the hydroxide. This is a primary niobium ore. And this, like I said, this is 80% of the world's niobium is coming from this one mine. And again, you see rare earth elements, ruby red. Okay, so now we're going to go to something that kind of started this all. It's like, what about Ukraine? Well, Ukraine has Archean shield and at least 50 Proterozoic carbonatite localities. So we know that they exist, and these are some of the things that are here in the critical raw materials. This rare earths here is this green areas, and titanium, iron, uranium, and graphite are major commodities. The mining for this is being done. It's being sold on the international market. Its financial resources are very useful for Ukraine, but a lot of these other deposits are known from Soviet geologic investigation, but they haven't been developed. The Ukrainians have kind of agreed with what the Soviets found and said, yes, we have them, but they simply haven't been developed. So the idea is for the United States and other Western countries to provide the technical know-how and some of the financing to help them get these mines on board. And I cannot see, and I couldn't find anywhere that could tell me whether this is really what the extent of this is. There are some geologic sources that say, yeah, it's not much. And the other ones just say, hey, it's the same kind of rocks that we have again and again and again all over the world. Of course, they have the resources. They just need a lot more. It just needs a lot more research. Well, what is really important about Ukraine is that Ukraine does have Archean shield, and it does have all these mine zones, but what else does it have or doesn't have? It's not covered with glaciers. It doesn't have permafrost. It's a relatively mild climate, especially down here on the Black Sea coast. And a drawback is the very, very thick, rich soil. The thick, rich soil makes it, of course, a tremendous agricultural location. There's many people who are not interested in having mining resources developed any further in Ukraine because they don't want the agricultural soils damaged or taken out of production. And there's a point to that. And it's also an overburden that you have to move. But in terms of the locations being accessible by transportation, yes, we got that. Accessible, no permafrost, no glaciers, no remoteness, we got that. And we also have the Black Sea ports here to move large materials out relatively inexpensively. So this could certainly be a win-win for the country. But is it something that's ready to go right now? Absolutely not. Okay, I think that is it. And here is one more picture. This is the aurora that came down all the way almost to Jacksonville, Florida, a little bit earlier in the year. And so the aurora that they saw up in Yellowknife that night was purple. It was very, very beautiful. And I'm sorry that I do not have that picture, but it was so pretty that it's copyrighted and being sold. So I am happy to answer any questions that you might have.
Could I ask a question?
Yeah.
Given that you said that the rift zones may potentially have some of those minerals, the mid-ocean ridge down in the Atlantic all the way up to Iceland, could it be potentially rich in any of that kind of minerals and geology?
A source of rare earth minerals is definitely suboceanic. Okay, there's a lot of locations that most of your mid-ocean rift material is basaltic. It's not carbonatite, but there's a lot of places where there's heavy mineral sands. Sands have washed into the ocean and heavy minerals have concentrated, because there's one other type of deposit that I didn't really want to talk about because it doesn't provide, it's not particularly interesting for a mineral club, which is that some of the primary ones in China are iron absorbed clays. So there are places where, such as a laterite soil in the tropics, where it's very, very warm most of the year and it rains and rains and rains and rains. You would see that laterite soil is really, really red and it doesn't have much in it left, but like aluminum and iron oxides. And it's what you use, you get bauxite, you use it for aluminum ore. Well, then in certain places where there's some of those, say those Archean rocks have been eroded and washed, there'll be deposits like right offshore or deposits in lakes and streams and stuff of sediment. And in the case of China, it's mud. It's mud that's rich in rare earth elements. So they mine the mud and they get them out of there. So mid-ocean ridge, not so much, but lots of other places, around ocean islands, there can be rare earth elements.
And are the rare earth elements radioactive or wherever they are close to thorium and what was the
Yeah,
other?
there's one that's radioactive, but that's man-made. That's promethium. That's something that's there was a, it's made in a particle accelerator when you bombard nuclei. So it only has a half-life of seconds or microseconds. What makes them radioactive is because the uranium and thorium are the carbonatite melts concentrate these, what I call the large ion lithophiles, and uranium and thorium, especially thorium, fall right into that category. They love phosphates. If you want to find radioactive stuff, look for phosphates. They love phosphates. They love fluorite. They love fluorite. They love anything with fluorine. They love anything that's got that very, very low temperature, late stage melts, concentrate these big giant ions, and the minerals that are forming are just as happy to take thorium as they are to take cerium. They don't care. They pick it right up.
Thank you. Thank you very much. Thank you it was very nice presentation. Thank you.
Thank you.
So I've got a question. You mine the ore, got the ore that has, say, a half dozen rare earth elements. Where's the processing then? I'm guessing China right now, they have the ore and they have the process.
Well, that's China definitely does a lot of processing, but Canada is doing that too. That Nechalacho mine is supposed to be completely vertically that I believe they take it to another province. I think it may go to Edmonton or something for processing, but it's not leaving Canada at this point, and they don't want it to, because the idea is, and we did processing there at processing is still done in California, but the actual mining is not done. Processing of rare earths is done in Australia too, where they have mines for them. And it's, I believe in Scandinavia as well. So the idea is to, separating the rare earths is probably one of the most difficult things that is done in mining. And the flow charts for doing this are very, very complicated. And there are some countries, I would put Ukraine in that category right now, and certainly most of your African countries with rare earth element deposits have absolutely no ability to process them.
Hello, Leigh, can you hear me?
Yep.
Oh, that was amazing. I'm jealous. That was the best talk I've
I
ever
like
seen.
Harold. He's a ceiling.
What I wish I could steal your slides. That was
Oh,
fabulous.
you can have them. I don't care.
They were amazing. I mean, I don't know what to say about that. I'm really into geochemistry, so, and you never see that in a talk. It's always pictures of fluorite or whatever. That out of sight, girl. That was really amazing.
Well,
You've been
thank
around
you.
too, right?
It could certainly be improved.
I don't know about that.
I couldn't, I'd like to have a little bit more in there, but I'm getting up against the wall here with these things not being able to be emailed.
Yeah, I can
You
imagine.
know, the files are getting large. It would be, if you do ever get back to having your meetings, please let me know. I do,
Yeah. Well,
I do own a farm in Frederick County as well.
oh, okay. I was going to ask you where you're from. No, I'm a
Well,
visitor.
I live in North Carolina, in the Outer
Oh,
Banks,
okay.
in Buxton.
Yeah, they have a
But
nice.
I was born in Washington, D.C., and I grew up in Montgomery County and in
Oh, okay.
Frederick County. And so my brother and I have inherited our family farm. So I have we have part of the Frederick County side of Sugarloaf Mountain.
I think I know where that is. Yeah.
on
yeah.
Park Mills Road. If you know where, anybody who knows where Lily Pond's Water Gardens is,
Yeah.
it's right near there. It's a popular place for
Yeah.
people who have koi ponds and such.
Yeah. Yeah.
I have a question for you,
Mm-hmm.
Leigh. With the growth and demand for rare earth elements for all those applications, what countries do you expect are going to increase their production of rare earth elements going forwards?
Well, that's not the only location in Canada. That mine is going online, and that mine has, Nechalacho mine has 9% rare earth oxides, which is one of the richest findings ever. So that is not going out of business because Canada, you know, Canada is very similar to United States in terms of its use of technology and its use of cell phones. And, they manufacture a lot of electronics and such. And they have a large defense industry, as we do too, not quite as large, but large enough. And so they also have deposits in Labrador and Quebec that are functional and going to be increased. Australia is working rapidly to find more locations. Uh-oh. What happened? I've lost you all.
We still
We
see
still hear you
fine.
and see you.
Uh,
So
The
you
way,
you talk.
Okay, that's okay. We're good.
Yeah.
It wanted to do something else. Um, China's not backing down either. They're going to continue. But the question is, does Mountain Pass Mine reopen with controls for the radioactive elements? That's a yes or no. Because, and there's other and do we start looking at placer resources? Like I said, some of these sedimentary resources where the heavy metals are concentrated. I don't know if you've ever seen, walked along the beach, for example, where I live in the Outer Banks, and you see the some of the red sand. You see the reddish brown sand. If you reach down and scoop it up, it's very, very dense. It's mostly garnet. It's garnet, zircon, ilmenite. It is a heavy mineral sand that's washing out from the Appalachians in Piedmont, and there's layers of it in the sand dunes. Well, there's many places in the world where this heavy mineral sand is quite valuable. It's a source of zircon, it's a source of niobium, it's a source of rare earth elements. It's expensive to mine and it's expensive to separate, but it might be that's what needs to be done. And then of course, the there are resources in Russia. There's resources in Russia. The Russians are going to continue to develop the resources, and they may come around, stop what's going on now, go back to a peaceful regime, in which case Russia and some of the other Scandinavian countries, especially up in the Kola Peninsula, will be providing the rare earth elements for most of Europe, because Europe is desperately in need of them too. Again, their technology sectors are very, very well developed. And you can even just look at all the different colors that we have on the screen. Somebody's coming up as L and coming as J. These plasma TVs and all the touch screens that we take for granted these days, they all use rare earth elements to get those bright colors. You can think of it like this. They're similar to you were talking about the diamonds having the different colors because you have you have some trace elements in there, and they vibrate in the crystal lattice and give you something in the visual wavelength. Well, we make a lot of ceramics or synthetic minerals, and we dope them with these rare earth elements because they're very heavy, and they do the same thing. They take something that's just clear or very, very faintly colored, and they turn it into something that's, violet, just gorgeous. And it's like, oh, okay, well, the Google, it's right here on my screen, the little Google logo that comes up. It takes rare earth elements to make those colors.
Thank you. Really enjoyed your talk tonight.
Thanks.
I have one comment here. Can you hear me? Roger Haskins. Yeah, I'm a retired economic geologist, but About 10 months ago, it was announced in Wyoming in an open pit coal mine that the bottom 30 feet of it were so rich in rare earths that the coal could be mined for the rare earths on its own and sent off to processing somewhere. And the coal company is now actively planning to remove the rare earths and send them off to somewheres. But it was quite an interesting situation. It's right on the bottom 30 feet where it's up against the water table, and they're trying to determine where the rare earths came from. But it's highly concentrated in that bottom 30 feet. So keep your eyes open.
Yeah, I remember reading about that. I probably should have put something in there because it was a little bit unusual. And that is another type of resource. I don't remember whether that was a hard rock or a placer type of source.
No, it's a coal mine. It's in
Well,
situ.
sometimes there's stuff at the bottom of a coal mine. You know, you got how
Right.
you have your different, you know, you have your shale and you have your coal layer and then you have your limestone layer and it cycles through. But I will look into that. Any resource in the United States right now, I think is fair game. Especially if we want to move some more of our chip manufacture and stuff to this country, then the rare earth elements, we don't have a choice. We have to have that those products have to be available. We cannot rely on importing them from a country that I don't want to call would be hostile, but is not going to, their priority is themselves. Their priority is not to supply us. They know perfectly well that it's gotten a little bit better, but at one point, I think I put that in the abstract, 97% of the rare earth mining was being done in China. And 97% of the processing too. And so they could charge what they want.
Could I ask
Yes.
Tom Tucker, would you like to ask a question? Your screen keeps coming up.
Yes,
as if-
Betty, just as a casual side comment, about 3 weeks ago, there was an article published in Mineral News, a little Tony Nickisher's newsletter from down in Charlottesville, on the minerals from Stoudemire Branch in Augusta County. It's about 20 miles from where I live. He published a list of 92 species that we're finding in this little syenite rock outcrop. And of those 92, a goodly number, and I can't quote, haven't counted them, but there are a good number of thorium and yttrium and lanthanum species that are in that syenite. Of course, volume-wise, they're insignificant. They're not ever going to get mined or anything like that, but it's a curiosity in our backyard.
Well, there is that is true. There is that part in central, more like central Virginia, that is known. I mean, it was considered to be a uranium resource for a long period of time, and they went back and forth as to whether they were going to have uranium mining there, and it turned out that they don't. But some of those rocks are eroded, and that is the result of that is that northeastern North Carolina placer deposit of rare earths. So that is one way that something like that doesn't seem economic can potentially become economic if you want to mine the rare earth sands. The problem with that is, you know, a lot of times the separation of that is very difficult, just as in because and they can be very, very hydrated from sitting and not particularly valuable. But Australia has large resources of heavy mineral sands, and especially in Western Australia, around the Perth area. There's some, I've been to many years ago to a mineral sand place there, and it's a very, very viable operation for them.
Thank you. And Teresa, Joanna, I see you've got your hand up, and there's a lot of people who have unmuted, but Teresa, a while back, had raised the question, does mining of these minerals cause environmental issues?
Well, there's no mine in the world that doesn't cause environmental issues. I mean, that's just the way it is. And the Nechalacho mine in the Northwest Territories is right at the lakeshore, so people are going to have to keep that in mind. I said some of the gold mines there, such as the Giant Mine, that was the mining museum. It was not the mine. They were closed because of the use of arsenic to separate the gold, and arsenic and the use of mercury in the past for gold mining to separate the gold out. But these things they became aware of it. The Canadian government, and working with the mines, has fixed most of the problems there. They've done environmental remediation. They have better ways of operating. And so I said that mine is a consortium between a private company, but I think it's Cheetah Mining, but the private company has agreed to work with the native community and hire a certain percentage of them to do it. And they definitely want the work, and they definitely want to do the mining. And the rare earth elements are actually much more concentrated than gold in the ore, so not as much processing is required. One of the major problems with all the different separation is that it's difficult to do, and that was one of the problems with the mine in the Mojave Desert. It's difficult to do without a lot of water. You need a lot of water. So being at the lakeshore is great for them. I would say that many places where in the shield rocks and the carbonatites, there's not much else going on. There's plenty of, it's far away from where people are. It's far away from agricultural areas. It's going to be all right. And then there's also Brazil. Brazil mines with environmental standards that are not the same as other countries. You couldn't do that in France. You couldn't do it in Great Britain. You couldn't do the US and Canada. They have much less regard for their environment because the resources that they have are so important to their country's economy. And they say, well, we couldn't do anything for anybody if we didn't utilize these resources. And I know that Araxa mine that we saw in Brazil has plans for only expanding in the future. They want to be the world leader, period. They already are for niobium, but they want to be the leader for other things too. But there's no way to mine anything without some type of environmental impact. It's just going to have it. The question is, can you mitigate it? Can you make sure that your risk, you look at the risk equation, there might be some risk, but the benefit to society is much, much greater. If you get to the point, we're not in a position to say that we can't use these elements. We don't want to, if we want to stop utilizing all this technology, then we can stop mining. I don't think anybody wants to go back that way.
Leigh, as a follow-up to the vertical integration from mining, you've got the ore and you do the processing. Say we have a chip plant here in the US or whatever, and we've got the ore processing. What's next after processing to the chip plant? Are there more steps where we rely on other countries?
We can do, I have to admit that I didn't spend a whole lot of time on the processing because it would have taken up probably an hour to go through. We are capable of doing everything. Okay, your silicon that's on the chips, for example, that's deposited from like silicon fluoride. Okay, it's deposited from a gas. And our technology for doped ceramics, to use for laser crystals, to use for LEDs, to use for custom crucibles and high temperature ceramics is as good as anybody's. We're world leaders in that. So we can get that done. some of the problems that we have is that when you rely on the easiest and the richest sources of things, the carbonatites, again, I said it's mostly the light rare earth elements. The heavier rare earth elements are less common in harder rock places, or of course in the deposits in China, the ones that are in the clays. So the world is looking for more sources of the heavy rare earth elements and not so much of the light. The one that you see showing up again, the CE, cerium, there's actually the market is fully, there's plenty of cerium. Like there's no shortage of it whatsoever. That most of what's coming up from the rare earth mining is cerium, and we have enough of it. We don't need more. We need more of these heavy rare earths and more of specialty rare earths. We don't need much europium either. We can utilize it, but the thing about europium is because it has the 2 valence, the europium goes into rock forming minerals. Europium goes into feldspars, for example, and it was one of the ways that we figured out that the moon had some sort of differentiation, had other than it, because it doesn't really have the magnetic field that we have, but some rocks were looked at, some Mare basalts and some anorthosite, which is a high calcium feldspar, were looked at, and you could see that one part of basalt was lacking europium, and then there was a great big spike in the feldspar, meaning that it picked it up, right? It took it out of the basalt and it picked it up in the anorthosite, in the white rocks that you see on the moon. So this is a well-known thing in planetary science, is looking for the europium anomaly. So europium, we can find that in places that if we need it. It's some of these really strange ones toward the end of the periodic table that are what people are looking for.
Leigh, that carbonatite volcano in Tanzania, I think, is really interesting. And I'm wondering, are there deposits with REEs that are essentially old carbonate lava flows, or could a volcano itself be a primary source of REEs?
Well, I think that place in Tanzania too is famous for a lot of other things. It shows up on, trivia nights and world's greatest disasters and things, because there was a periodic mass killing of flora and fauna, and it was from, huge amounts of carbon dioxide that were spewed out of the volcano, just huge amounts. And nobody knows why that's the only example. There was other places in the Rift Valley where these volcanoes existed, but that nature light that's showing there, it's kind of like what it is it's that those piles were great big piles of sodium carbonate, and it's like putting Epsom salts or something out, and it rains, it washes away. So it's constantly being washed away and constantly being eroded. And everybody's on the lookout for more of those volcanoes, but that is the only active volcano like that that's known. So yes, those deposits could certainly happen.
It's also one of the only volcanoes that somebody has been known to fall in and be pulled out alive.
Was that you?
No, but it's not very hot. And also all the gas in it. So some dude actually fell into, there's a great story. Some dude fell into this thing and they were able to pull him out alive. So
Come to think of it, I remember that now. Well, that's exactly what I'm saying. It isn't very hot.
Very hot.
Because it's so filled with volatiles. It's very, very low temperature magma. It's like someone mentioned Kilauea. It's absolutely nothing like that. Okay, you fall in Kilauea, you can't even get close enough to fall in. Okay, it's not happening. So yeah, that's a strange situation there. And it's probably worthy of an entire lecture. Some people did say that they love volcanoes, but the mineralogy of it, in terms of your mineral collecting and your origin of your different minerals deposits around the world, is fairly minimal. Because like I said, they see these cones form, and it's mostly sodium carbonate. And when it rained in the rainy season, it just all washes away. That's the feeling. I mean, we got a lot of sodium in the ocean somehow, and that's that's the way it started.
Anybody have any further questions for Leigh?
I think Joanna has been waiting a while.
Oh,
Yes.
you have, yes.
Oh, but you need to unmute, Joanna.
Yeah, I
If you're-
don't hear it.
I have no idea what you're talking about, Jeff. Well,
Oh,
we're going to have an emailed question to you, Leigh, at some
And
point here.
you haven't watched the Star Wars movies.
I have. In what way are we referring to Anakin Skywalker, my good friend?
He falls into a volcano and
Oh,
is
yes, yes, yes.
drowned and becomes Darth Vader.
Well, they
Yes,
kind of
yes.
do that in that Jurassic Park movie too. That lava's coming right after them, and they're running after, and they're
And I also,
chasing them down,
yeah,
and they
and
don't.
I
It doesn't
yeah.
occur to them that it's so hot, even close to it, that they're not going to live. But
suspension of disbelief.
so Joanna has unmuted now.
Joanna has unmuted, has
Yeah,
returned. The question.
yes, sorry. I just got a call while you were asking me to unmute. I had a couple of questions since the whole California thing came up and California. Do you know if regulation-wise, if we reach the point that we cannot get rare earth minerals from anywhere else, can the federal government call it like an eminent domain kind of thing and force California to allow mining there? And that's my number one question. And my number two question is, because you mentioned something about bauxite, given the quantity of bauxite in Jamaica, are we suspicious that this is another source that around Jamaica may be rare earth minerals also?
the bauxite from the laterite is mostly kind of a paleo soil type of thing. I'm not aware that there's too much in the way of rare earth elements in Jamaica. That's mostly those type of aluminum deposits occur because it's been very, very humid and very, very rainy in the soil's everything else is washed out of the soil. All the iron, all the manganese, everything is gone. So not necessarily in Jamaica. As far as eminent domain is concerned, I'm not an expert on the legal thing, but my feeling is that you almost always need a private company to do the mining. The federal government is no good at that kind of stuff. And if they get involved in it, they can certainly allow it, for example, the way that they allow people to utilize national parks, to utilize forests for ski areas and things like that. If it came down to it, where that was the quickest and easiest way was to reopen that mine, it'll get done. It will get done. There's going to have to be controls on the radioactive elements. You can only control it so much, but honestly, they just used to do very little about it. They knew it was radioactive and they were like, okay, fine. Now, I'm not even sure how you would even go get people to even work there. You know, they would say that it was dangerous and you couldn't do this and you couldn't do that. But if it got to be only our source, yes, it would be used. It would have to be utilized. Hopefully, the sources in Canada will provide enough basically for North America. And also Brazil is a good ally for us in terms of mineral resources. They know their markets and they're a good ally for us. And we don't foresee anything in the reasonable future where we wouldn't be able to procure rare earths from them. But, you know, stand in line because they sell to lots of other countries.
And compared to what they make financially what they benefit from the gemstones they produce versus the rare earth minerals. If they had to, if there was a competition between what should they go for and what should they mine and what they destroy to mine the other thing, which one makes more money for them, the rare earth?
Oh, sure. Yes. There might be, something might be particularly valuable in terms of a gemstone, but the market is still relatively small. I mean, what is the market? The greatest geologic resource market is sand and gravel. I hate to say it, but it's true. And iron ore is way up there too, because we need so much iron and so much steel. But there's plenty of people in this world that made all their money off sand and gravel because people need cement.
Yeah.
People need cement and people need paving and people need driveways. And so the volume, there's many other things that Brazil produces too, but niobium isn't just one of those things that's utilized in, you know, cell phones and small amounts to dope crystals. Niobium is a critical component of high-tech stainless steels and metal alloys for aircraft and stuff. It's utilized in probably more than any of the other rare earths are. So that is a huge market for them. There's certain types of military applications that use specialized stainless steel and fighter jets and stuff. And there's no niobium has to be used. There's no substitute for it.
Okay. And you mentioned something about the moon, and do we think anything on the moon can be viable for rare earths, and also on Antarctica?
Well, Antarctica has a shield and Antarctica has resources. We just haven't got around to really utilizing them, but everybody knows that they're there. We just have it's the accessibility factor. Okay.
Mm-hmm.
How do you go about setting up a mine there, running a mine? You need a lot of liquid water to run a mine, so you have to start melting stuff all the time. Then you got to get the stuff out of there and you got to get the people in there. It's the same problem that Russia has with many of its Siberian resources. It probably has more resources than almost any country in the world, but a lot of them are in the very, very far north. And one of just the transportation system alone makes, I mean, the word ore is an economic, somebody's an economic geologist. Yes, it's an economic definition. It's not a geologic one. An ore is only an ore if you can make money off it. If it gets if it gets to the point where it costs so much to mine and process it that the end product you're losing money making, well, then it's not an ore deposit before. It's a former deposit, or it's a resource that might be utilized at another time. So that would be your problem with trying to operate in Antarctica, is that you would end up, it would cost you so much more than the product was worth. We like,
and it has to be fresh water. It cannot be
yeah, you're not going to be you can't use salt. There might be some washing and stuff where you could certainly use this ocean water, but by and large it's going to corrode your equipment.
Yeah, and your metals too.
And the moon, is the moon a possibility?
We've reached the 9
The
o'clock.
moon's a possibility, but again, what is the definition of ore? How much does it cost to send that stuff back?
Yeah,
it's not that valuable.
No.
We have reached the 9 o'clock hour.
Thank you. This was lovely. Thank you so much.
You're welcome.
I appreciate everybody. We have to release Leigh from MSDC bondage here.
Thank you, Leigh.
We appreciate you.
Thank you.
Again. And good seeing everybody.